So I can hardly believe it's been 3 years or so since I last did one of these, but here we are. So slightly different theme this time, but same planet, which is planet Mars, and thinking about structural glaciology on Mars, and in the context of a kind of new era of Mars exploration that is emerging, which has a very icy focus. So it seems that the future, or the near future, of Mars exploration missions is quite glaciological. So hopefully in this talk I can pique your interest in some interplanetary glaciology. But we're not actually going to start at Mars. We're actually going to initially go to the inner solar system, because I basically just want to emphasize that even though the inner solar system is very hot, it's an icy place even there. The solar system has rather ubiquitous ice throughout it, really. And even the innermost planet Mercury has ice deposits, or is thought to have ice deposits. And that's because Mercury, unlike the Earth, is not tilted towards the sun. It actually has effectively a 0-degree obliquity. And on planets that have impact craters, that means that at the poles, impact craters don't receive any sunlight because they're big holes in the ground, and the sunlight is coming in very obliquely. And so there are actually permanently shadowed craters on the planet Mercury that are thought to contain ice. So even though the maximum temperature on the surface of Mercury is about 420 degrees, in permanently shadowed craters, because there's no atmosphere, the temperature can get down to about minus 190 degrees C. So it's actually thought that there is water ice here. And believe it or not, it's actually been observed from Earth as well as from spacecraft. So I find this picture absolutely incredible. This is a composite image from the Arecibo Observatory in Puerto Rico, which very sadly has now been decommissioned because it was damaged in a hurricane, but it did amazing science while it was up and running. And this image on the right-hand side, you can hopefully make out structures of impact craters. This is the pole of the planet Mercury, and those bright areas are radar reflections, which are thought to be ice deposits. So I recommend going to have a look at this paper, which it absolutely fascinates me that we can see these sorts of things from Earth. So there's ice on Mercury. There's also perhaps ice on the Moon. So the Moon also has these permanently shadowed impact craters. This is a famous one called Shackleton Crater, which I'm sure needs no introduction to the International Glaciological Society. This is a really fascinating crater, and there are many others besides, shown on the right-hand side of the screen, which are thought to host some amount of water ice, which seems quite alien on our own moon. And we're actually going back to the moon. So the Artemis program is a big program with several missions of increasing ambition and complexity, aiming to return humans to the moon this decade. And this is an image from Artemis 1, which was the first mission in this program, which in 2022 was an uncrewed mission that orbited the moon. And this is showing the European Space Agency's service module taking NASA's Orion spacecraft around the moon. Now, the Artemis program in itself will do incredible lunar science, but it's also, in a way, a dress rehearsal for Mars. We're kind of preparing for the next giant leap in our solar system to eventually take humans onwards to Mars. And in all of this, this entire pathway, as we'll see later, ice is a really key target, and that's basically why I'm here today. So let's go to Mars then. Mars is an icy world, despite being known as the red planet. It's got these amazing polar ice caps that are between 1 and 3 kilometers thick, and their combined water ice volume is about the same as the Greenland ice sheet, or thereabouts. The South Polar Cap also has a thin layer of CO2 on top of it, and that's actually as a result of the present day climate parameters of Mars. So Mars's atmosphere is composed of primarily carbon dioxide. So it's about 95% carbon dioxide, but it's very thin. And you don't really want to go there on your summer holidays because it's extremely cold, and this is why it's such an icy planet. So its mean annual surface temperature is about -63 degrees C, but it does get quite warm at the equator at the height of the day. It can get up to 30 degrees at the equator, but this doesn't last very long, of course, and there are huge temperature swings. And in winter, the polar temperatures can get down to -130 degrees C. Now, in the present day, the sort of visual distribution of ice on Mars, as you can see in this photo, is very similar to what we see on Earth, i.e. we have these big polar ice caps. And that's because Mars is currently quite similarly tilted towards the sun as the Earth is. So unlike the Moon and Mercury, we have a tilt towards the sun of around 25 degrees C, 25 degrees for Mars. And this means that the poles are kind of the coldest place, and therefore the polar caps are stable. The atmospheric pressure on Mars, however, is very low because the atmosphere is so thin. And so unlike Earth, where the distribution of ice is controlled by the temperature relative to the melting point for the most part, on Mars it's actually controlled by the sublimation point. So this 6 millibar atmospheric pressure is below the triple point of water, just below it, not very far, but just below it. And that means that actually liquid water isn't stable on the surface right now. And so ice tends to turn straight to a gas, and gas tends to turn straight to ice without going through the liquid phase. And so rather than thinking about melt controlling the distribution of ice, we're thinking currently about sublimation. And this is very nicely illustrated by this video. This is a low pressure Mars simulation chamber at the Open University in the UK. And this is just liquid water at room temperature in under Mars's atmospheric pressure. And so it's quite striking to see this actually in action. This is just water boiling in at low pressure. So if liquid water did occur on the surface, it would be doing this in the present day and wouldn't stick around for very long. But Mars is a very dynamic planet, and those parameters that I've just shown you may not have been stable throughout time. And that's because, unlike the Earth, which varies in its tilt by about a degree between interglacial cycles, Mars undergoes really large swings in its obliquity. So this plot on the right-hand side is a reconstructed obliquity history for the last 20 million years of Mars's history, and the present day is on the right-hand side. So in blue, you can see the last 5 million years or so that Mars's obliquity has actually varied really severely between about 15 degrees and 35 degrees, around an average of about 25 degrees. And this results in a transition in the stability of ice, or it's thought to have resulted in that. So as you increase to about 35 degrees or so, the polar caps become unstable because they receive too much solar insolation. And it's actually thought that the mid-latitudes are where ice was preferentially stable, resulting in mid-latitude glaciation and loss of ice at the poles. And you can see that we've had several cycles through this obliquity over the last 5 million years or so. And this is thought to be recorded in the polar ice caps, in layering in the polar ice caps. So this is a really striking potential climate record on our neighboring planet. And this is a radargram from the orbital ground penetrating radar called the Shallow Radar Instrument on Mars Reconnaissance Orbiter, which is doing incredible science at Mars. And so the bright white lines that you can see on this map are probably dust layers, and then the dark areas are water ice. And so these layers are thought to record those cycles of climate change on Mars. And it's this kind of behavior on Mars that means that ice is really a fascinating target for the next generation of missions, because we're really keen to reconstruct global scale climate changes of another planet and how the atmosphere has changed over time, and also search for microbial life. So there's always been this mantra of follow the water if you want to look for life. Well, where better to follow the water to than ice, because ice has potential to turn into water if the correct conditions arise. Ice deposits are also of real importance for human missions, which are on the cards and are being planned. And that's because they probably need some amount of in situ water resource basically to generate enough rocket fuel to come home again. So some amount of in situ water might be required for those missions. So there's a really strong case to go to ice deposits on Mars for science and for engineering requirements of such missions. Now, if we're going to go to Mars with such complex missions, we might not be aiming for the poles initially, at least. And that's just because the conditions there are really harsh. There's this deep polar winter, but it's also really hard to launch back home from the poles. The tangential velocity of the planet tends towards 0 at the poles, whereas at the equator, the planet can help you to launch out of the planet's gravity. So basically, we probably don't want to go to the poles initially, even though they've got this really tantalizing layering in the poles. So we probably want to aim for somewhere lower latitude. Now, fortunately, Mars helps us in this regard because those who were paying attention to this plot will have seen the big red area, which actually shows that around 5 million years ago, which is thought to be at the approximate age of the polar caps, there was actually a shift in the mean obliquity of Mars. So there were still these big variations, but rather than being on average around 25 degrees, there was a shift to around 35 degrees. And as I said earlier, this is when we tend to see a preferential stability of preferential stability of ice at the mid-latitudes. And when you go up to about 45 degrees, in fact, you actually start to get equatorial glaciation, of which we also see evidence. And the ice that was deposited during these higher obliquity episodes is actually still preserved on Mars today, buried in the ground. So a really extensive indicator of buried non-polar ice on Mars and ground ice on Mars is extensive polygonized terrain. So the middle panel here shows a view from the Phoenix lander, which landed on Mars in 2008. And it shows these beautiful fields of polygonized structures as far as the eye can see, which is very similar to polygonal pattern ground seen here on Earth. And Phoenix actually scraped away the surface layer of soil. It's only about a couple of centimeters deep. And as you can see on the right-hand image, we've got these bright exposures of ice. And the bottom right-hand image here actually shows exposures of larger exposures of ice that were formed when the retro rockets from the landing actually cleared the superficial material. And you can see that these are beautiful slabs of ice just beneath the surface. It's really tantalizing. It's very close to the surface. Now, Phoenix was really pioneering, really. But since then, we've got an incredible fleet of orbiters that can actually help us to see these buried ice deposits from orbit. So a particularly useful camera is the HiRISE camera, which is a 25 centimeter per pixel imager, which actually helps us to see natural exposures of ice from orbit. So in the middle here, you can actually see more of that polygonized terrain in the top image, and it's actually been impacted by a small fresh impact crater. And that impact has exposed ice from within that polygonized terrain, which then disappeared over time because of the aforementioned instability of ice at these latitudes once it's exposed at the surface. Now, the bottom image also shows incredible ice cliffs on Mars. So this is a buried ice cliff that's about 100 meters high. So this is really high purity ice, and some of you might be able to see boulders just at the bottom of that cliff. And that cliff is actually retreating, or is thought to have retreated, because once it's exposed, it starts to sublimate. So those boulders may have fallen off of the top of the cliff as the ice retreats across the landscape. Now, you have to be quite lucky to see these exposures still, because you basically have to spot an exposure with like a fresh impact with the relatively low resolution camera. I say low resolution, it's still 6 meters per pixel, which is quite incredible. And then re-image it again with the high resolution camera to see whether there's ice there. And that's all competing in time with the sublimation process. So while these are relatively rare, there is actually a growing number of observations, and the spacecraft team is becoming really good at getting the camera all sorted to take these high resolution images. So this is really exciting stuff, and fascinating to see these ice deposits so tantalizingly close to the surface. We also have one of my favorites, which is something that we call viscous flow features that are actually thought to be debris-covered glaciers, put more simply. So we have three main types, three main large types. We have these topographically unconfined apron glaciers that you can see on the left-hand side, rather like Piedmont glaciers here on Earth. We also in the middle have large valley glaciers that flow down 100-kilometer long valleys in some cases. And then on the right-hand side is a very common feature on Mars, but one that's less common on Earth, which is a glaciated impact crater. There are thousands of these on Mars because there are so many impact craters around. And we can actually use that orbital radar system to see the beds of some of the larger glaciers. Currently, this is limited to the apron-like glaciers just because the topography is a bit less complex there, so you don't get as much radar clutter. But as you can see in this image, we've got beautiful detections of the beds of some of these apron glaciers, and this has been used to constrain their ice content. And it's been found that they have up to 90% ice content by volume, and the surface debris layer is probably about probably less than 10 meters thick, because that's the resolution of the radar and we can't see that interface, so it's probably somewhere in that depth. And so they really are very analogous to debris-covered glaciers on Earth. Of course, some smaller features may have lost more of their ice and may have transitioned to rock glaciers today, but we do have a very large number of these really voluminous features still, and thousands of debris-covered glaciers on Mars. It's also possible to deploy another technique from orbit to detect shallow ice. So the radar that I just showed you has a vertical resolution in free space of about 15 meters, which reduces to 10 meters in ice. So that means that we can't really, with that radar, see the upper 10 meters. However, we also have a couple of orbital neutron spectrometers in orbit, and these are really useful instruments for seeing the composition of the upper meter of the surface. So neutron spectrometers can detect water equivalent hydrogen in the subsurface. And so basically cosmic rays can penetrate into the surface of the planet. They excite hydrogen in the subsurface, which then releases neutrons that are intersected by the spacecraft, and that the number of neutrons released is counted, and therefore you can back calculate how much hydrogen there is in the subsurface. Now, at low weight percentages, that could be hydrated minerals like clays. So on this map on the right-hand side, you can see blue areas, and at the equator, the sort of low values are probably hydrated minerals. However, when you reach a weight percentage of water equivalent hydrogen that's more than about 25%, that's really best explained by ice that's present in more than 50% by volume, so massive ice effectively. And in the map on the right-hand side, you can see that this is basically extensive across any latitude greater than about 50 to 55 degrees. So at high latitudes on Mars, we've got massive ice deposits in the upper meter of the subsurface. And this correlates really nicely with the distribution of those polygonized terrains that I showed you earlier. Now on this map, I've also plotted the locations of those debris-covered glaciers, and you'll see that they actually occur at lower latitudes, so the mid-latitude band of Mars between about 30 and 60 degrees north and south. And these aren't detected by the neutron spectrometers because we think that the ice is deeper. So it's closer to the equator, it's a bit warmer, the ice is not stable as in at shallow depths, and so it becomes a bit deeper and is out of reach of the spectrometers. However, that's where the radar comes in, and we can constrain the ice content. So we have really extensive ice deposits that actually affect around a third of Mars's surface. So this, I'm not joking when I say Mars truly is a glacial world. And this means that glaciology is really key to the future of Mars exploration. And there's actually a pathway to human exploration being developed in which ice missions really are the centerpiece. So as I mentioned before, current instruments on the spacecraft that we currently have or have had in the past are kind of optimized for sensing ice that's shallower than 1 meter or deeper than 10 to 15 meters. So shallower than 1 meter is imagers and neutron spectrometers, and deeper than 10 meters is the ground penetrating radar. And this means that the 1 to 10 meter depth zone, we can make inferences about, but we know less about the specific ice properties in that depth zone. And yet this is the zone that's really critical for surface missions that might aim to access ice. And that's for a couple of reasons. First, practically, you probably don't want to be drilling too deep on Mars, on Earth, let alone on Mars. But also the upper meter is heavily irradiated because of Mars's thin atmosphere. It receives a lot of radiation. And so if you're searching for life, you probably need to go a bit deeper than a meter, because any biosignatures in that upper meter are probably going to have been destroyed by the radiation environment. So that 1 to 10 meter depth zone is really important. And this is where a new mission concept comes in. This is the International Mars Ice Mapper Orbiter mission, on which I served on a measurement definition team last year, or the year before actually now that we're in 24. And this mission concept would take the first synthetic aperture radar to Mars. It would be an L-band synthetic aperture radar that would be capable of resolving that upper 10 meter zone. And there's potential for it to also carry additional instruments, including, for example, a VHF radar sounder that could penetrate a bit deeper. And the overall aim of this mission would be to map and characterize the accessible near-surface water ice within the upper 10 meters of Mars's subsurface in the mid to low latitudes, those key target areas, to support planning for the first potential human surface missions to Mars. So this is really exciting to me. This would be an incredible mission, and I really hope it flies. There's also another potential mission concept on the cards. So last year, the US had their, every 10 years, they have something called the Decadal Survey, where they survey the community for scientific priorities for the next 10 years. And this, the Planetary Science Decadal Survey recommended that NASA prioritizes a static lander concept called Mars Life Explorer, which would have a drill on it to drill into ice deposits on Mars. So these are two potential ice missions in the near future that are very exciting, and watch this space. And the main thrust of today's talk, no pun intended, is that I think structural glaciology is absolutely critical for such missions, and we can actually start to progress this with the data that we already have. So why is structural glaciology important? Well, for many reasons, including accessing ice. Fundamentally, we need to understand the structure of subsurface ice, its layering, its lithic content, etc., in order to know what ice deposits might be accessible with technologies and to design the systems that might drill into those deposits. If we want to do good science at ice on Mars, we also need to, before we go, understand, at least initially, how we think environmental records might be configured in those ice deposits. And this is where structural glaciology becomes really important, because that really determines how environmental records might be configured. The other thing is habitability and search for life. Lithics in ice can really enhance its habitability. And so if we're not only interested in layering of ice, but also of layering of lithic materials within that ice, and that also comes under structural glaciology. The other thing is that for Mars missions, we could have to be quite industrious, and glaciers can be quite helpful in that they can transport materials from a range of source regions. So if we understand the transport pathways through glaciers, we could end up actually sampling sites that you can't actually get to, but the glacier may have transported material from those sites to a sampling location. And structural glaciology can help us to understand all of these things. And of course, as terrestrial glaciologists will know, but these images very clearly demonstrate, glaciers can be really complex. And so, this is just really fascinating science with potential to deploy it on another planet. Now, I'm not going to labour the point too much about meltwater in this seminar, but just to say that, of course, thermal regime is also really important on its own, but also for structural glaciology in terms of how much lithic content you might get in a glacier. And meltwater histories of glaciers on Mars is the topic of my previous IGS seminar. So do go and take a look at that if you're interested. And we also wrote that seminar up and with new updates in the recent IGS Global Seminar Series special issue in Annals of Glaciology. So if you are interested in meltwater specifically, then do go and have a look at those. From here out in this talk, we're going to assume that in the present day, these glaciers are completely cold-based and frozen to their beds. But what this talk and paper show is that some glaciers on Mars may have, well, there's indicative landform evidence actually that some glaciers on Mars have produced meltwater in the past. But let's assume that in the contemporary Mars system that they're not producing meltwater. So I want to highlight today a recent paper that we've just published in a special issue of Icarus. This is called The Internal Structure of a Debris-Covered Glacier on Mars Revealed by Gully Incision. And I was very pleased to see that around the same time, Katie Miles published a fantastic paper called The Internal Structure of a Debris-Covered Glacier in the Himalayas. So it seemed very timely that we were doing these on different planets at very similar times. So I want to acknowledge my co-authors on this paper, and in particular Neil Arnold at Scott Polar Research Institute, who contributed to the modelling in this paper. So as we've seen in earlier slides, glaciers on Mars have really complex surface structures, and they're very tantalizing, very interesting, and you can get lost in them for hours trying to work out what they mean. But fundamentally, they're very evocative of layering and flow. This is why they've been called viscous flow features, because they look like they've flowed in a viscous manner. And as with glaciers on Earth, this kind of structure on the surface inevitably manifests in their internal structure. I just can't see a way that it doesn't. However, as we saw earlier in the radargrams and also repeated here on the right-hand side of the slide, orbital detections of glacier internal structure have been basically elusive. The radars haven't picked up internal structure, certainly not internal structure connecting to the surface. There's a couple of near-bed detections in an early paper, but really nothing substantive that's really convincing internal structure throughout the ice masses. And this is obviously puzzling, but it potentially results from various limitations of the existing radar instrument. While the instrument is fantastic and has done great science, its resolution probably just isn't quite good enough to do internal structure of these smaller ice masses, unlike the poles where we saw it does really well. The other thing is things like surface roughness, steepness of layers, etc., etc. So currently with the radar, we're not really seeing much internal structure, but as a glaciologist, I'm pretty convinced it must be there. And just in case you're not yet convinced that it must be there, here's a couple of teaser images. I'll just let you admire this while I take a sip of water. So this is a segment of what's called the Hourglass Glacier. This is actually 2 crater-filling glaciers, and the ice is flowing from one crater into another. And here you can see beautiful structures, both longitudinal and transverse to flow. You can start to pick out potential flow units in these craters. If it wasn't bright red, you might think this was on Earth. Here's another example, also in an impact crater. This is from the Cassis camera on the European Space Agency's Trace Gas Orbiter spacecraft. This is a color camera that really picks out beautiful contrasts in the color of these surface structures. And the structures here are so diverse. So we can see in the middle of the screen really fine potential layering outcropping, and then potentially some deformation structure in here, crevasses, all sorts of fascinating structures that you could get lost in for hours. And that's just one segment of one glacier on Mars. So now that I've whetted your appetite, I'm going to take you to a site in a region called Nereida Montes, which is down in the southern hemisphere of Mars in the mid-latitudes. Actually, the glacier is on the side of a mountain that forms the rim of the large Argyre Planitia impact basin. So these mountains are forming the rim of that basin. And so the yellow star sort of shows where we're going here. And this is a 3D view of the study site. So this is a real digital elevation model of the site. And it's a 1 meter per pixel elevation model that's generated from two 25 centimeter stereo images. So we can really start to do really detailed analysis with such incredible data. We're going to try not to get distracted by those beautiful moraines on the right hand side of the image and focus on the areas where I've drawn some outlines for you. So here in blue we've got the glacier itself. This is a relatively small glacier. It's a few kilometers long, and it's sitting on the side of this mountain that's outlined in dark grey. And what you might be able to see in this view is that the glacier is actually incised by something called a gully. So you might be familiar with gullies on Earth. Well, they also exist on Mars, and they comprise an erosional alcove that you can see eroding into the hill slope, and then a chute that has transported that material down the slope. And in this case, the chute actually incises through the glacier on the hill slope. And then the material, or the non-volatile material, I should say, so the non-icy material, has then been deposited in a depositional fan beyond the ice margin. And this is incising through the glacier all the way from its head wall to its margin. So we're going to zoom in on that incision a bit more. So this is a 6 meter per pixel context camera image from Mars Reconnaissance Orbiter. And I'll just pause on this screen for a moment so that you can see the structures that we're looking at here. So on the right hand side, you might be able to make out a crevasse field. The gully channel is along the bottom of the image, incising from right to left. And then we have these amazing arcuate structures that curve around from the lateral margin towards the top of the image, and curve around and become flow transverse towards the ice margin. And when I saw this, I was actually at a conference with my co-author, Dan Berman, and I saw this from quite a zoomed out perspective, and I said, Dan, just zoom in on that incision, and I bet I can tell you what you're going to see. You're going to see inclined internal structures. And that's a bit of a spoiler, but I'll show you in a second. But you can actually, if you squint, see it at this scale, but we'll zoom in to a higher resolution image. So the black box now shows where we're looking at. We're looking at where the gully alcove intersects those flow transverse structures. And on the right-hand side, we've got a false color high-rise image. So this is 25 centimeters per pixel. And hopefully what you can see here, aided by the arrows, is some color contrasts that pick out distinctive banding that connects the surface structures to the interior of this glacier. So this is, I should say, this is a debris-covered gully incision, so it's become mantled by lithics, but we've still got distinctive color signatures that show structure within this outcrop. So I'll just pause there so you can have a closer look, just in case you haven't spotted them yet. But hopefully you can see that there are sort of narrow reddish structures within sort of a bluer ice mass. I realise I'm much more used to looking at these images than other people, so I don't want to rush. But we'll see them more in other images as well. So believe it or not, with the amazing elevation models that we have for Mars, we can actually start to take dip and dip direction measurements from orbit, which sounds quite outrageous, but we can. And so I did this, and this schematic shows the configuration of these structures in the wall of this gully. And this, as glaciologists, this is probably starting to look quite familiar to you. You can see that the layering transitions from relatively bed parallel up glacier and becomes more and more inclined as you head down glacier towards the margin. And so this layer that I've called L down actually is diverging from the bed at about 23 degrees and 11 degrees from the horizontal. So it's quite steeply inclined. And so this is an example of quite similar configuration of structures on Earth. So we think that the most likely analog for these structures is tilted layers within glaciers on Earth, such as upwarp layers or thrusts. So on the left-hand side is an image of debris-rich thrusts in Svalbard. The alternative is that it's just primary layering that's become upwarped rather than thrusts. And I think that for the Martian context, upwarping is somewhat more likely than thrusting, but we haven't ruled out thrust completely. So I hope this looks rather familiar to you. And I think it's quite evocative of these Earth examples. And so to explore this further, we actually deployed ISSM, which is a 3D ice flow model, to explore the stress regime of this glacier, to see if it made sense as a compressional structure that had potential to upwarp or thrust. So those structures, if you're not familiar, I should go back a second, those structures on Earth, if you're not familiar, actually form where relatively fast flowing ice from the interior of the glacier bunch up against relatively slow moving, often colder ice near to the ice margin. That induces compression, which drives either upwarping or thrusting or a combination of both. And so with this model, what we wanted to do is see if those structures occurred in a zone where we might expect that kind of flow compression mechanism. And so on the left-hand side, you can see a map of the reconstructed ice flow velocity in the horizontal component. So this is a 3D model that we input the surface elevation of the glacier and also a reconstructed bed topography that we derived by tracing around the ice margin and up the gully incision, assuming that the gully incision reaches the bed, which seems like a relatively secure assumption. So with that, the reconstructed velocities show kind of what we were expecting, which is that the velocity is relatively high up glacier, that's in yellow, and slower towards the margin, which is in dark blue. Now, I say relatively fast higher up glacier, we're still talking about millimeters per century because we're under very cold conditions here, assuming a mean annual surface temperature of 210 Kelvin, which is the contemporary mean annual temperature here. So this is assuming cold-based ice. Now, of course, these may not have formed under contemporary conditions, of course, but this is a conservative assumption for the moment. If we increase the temperature slightly, so by 10 Kelvin, we get a 5 times increase in these velocities. And if we increase it by 20 Kelvin to 230, we get a 20 time increase in the velocities. So the middle panel then shows what those velocities mean for the stress regime of this glacier. So we've got the horizontal component of the deviatoric stress. And in this plot, the blue areas are compressional. And hopefully what you can see from this plot is that those structures coincide beautifully with a really deep zone of flow compression. Now, this model result is a problem of ice flow geometry, not of specific climate parameters that we put in or anything like that. So changing things like temperature changes the stress magnitudes that we see, but not this overall pattern. So we still see this zone of flow compression coinciding with those structures, which seems to agree with this idea that they are induced by slowing down of the ice towards the ice margin and some kind of compressional process. So then on the right-hand side of the screen is a transect that just crosses the terminal part of the glacier, and the black lines are the velocity vectors. And what you can see is that the lines diverge up towards the surface right in the vicinity of these structures. And this again supports this idea that we've got some kind of deviation in the ice flow up towards the surface here, which agrees with that hypothesis. And we sort of backed out some figures for this. So at the temperature that we input into the model, a particle like a sand grain or something would travel through the thickness of the glacier here, which is about 40 meters at near the margin, in about 4 million years, which is obviously quite a long time, but it is not unreasonable for Mars. If you increase the temperature, that reduces to about 800,000 years, and that's actually less than the age of the approximate estimated age of the glaciers in this area, which is thought to be around 3 million years. So it seems viable that you could form these structures by this mechanism, even with a cold-based regime. And so taking a bit further here, what could this mean for ice sampling on Mars if we're thinking relatively hypothetically at the moment, but it's an interesting thing to think about. So many of you will be familiar with the kind of standard ice core approach, which is this vertical ice coring technique, which targets undeformed layers of ice, often near to the ice divide, in order to access nicely stacked age sequences. And this has obviously many advantages, but one disadvantage is that if you want to access older and older layers, you have to drill deeper and deeper and deeper. Now, this is obviously increasingly difficult on Earth as you get deeper and deeper, let alone on Mars. So as we move towards these more complex missions to Mars, we might need to get a bit creative and think about, well, are there other ways that we could potentially reduce the cost and risk of this kind of activity? You know, maybe it is going to be best to take a vertical ice core, but maybe there are other techniques that we could use as well. And so what this glacier kind of invoked for me is that we might actually be able to deploy more of a horizontal ice core approach that might mitigate the requirement for really deep drilling. So as I said, the kind of target is for a kind of 10-meter depth mission. Well, how extensive is the climate record that you could get from 10 meters compared to if you take this approach, which is if you have layers outcropping at the surface towards the margin, you're basically getting older and older layers outcropping. And so if you took shallow samples along a transect towards the margin, you could effectively reconstruct an age sequence of layers without the requirement to drill really deeply into the ice. And this is the case if those structures are upwarping structures. And this isn't totally alien. It has been applied in Greenland with a level of success. So this is just basically a plea that we may be able to deploy this horizontal ice core approach. So we should consider multiple ways of potentially sampling for ice on Mars. And then let's come back to think about the search for life. So if we're thinking about the glacier and potentially that those structures could be debris rich, which by the way is why we think they might have a different color signature, then they could be transporting lithic material from some depth. And deep in the ice is of significant astrobiological interest. There are several reasons for this, including the fact that deeper in the ice, you're further away from that surface radiation environment and the severe thermal cycling that occurs at the surface. And so this is potentially a more habitable environment than near surface environments. And so if we've got materials coming from those depths, then shallow sampling might be possible without actually having to drill to those depths. Additionally, it's important to understand the structures within these deposits because while ice coring and drilling might not want to go too near lithics because it could create drilling hazards, if we want to search for life, then we probably want to go somewhere near to lithics, like near to dust and things like that, because lithic component can enhance the habitability of ice by providing energy sources and can also promote microscopic meltwater films even below freezing. So there are potentially some trade-offs that we might need to start thinking about in order to maximize the return for both climatological reconstruction and life searching on Mars. And this is a really interesting problem. So there's a couple of examples here. I've just explained that lithics, good for habitability, and even in ice cores, like they can serve as chronomarkers and provide interesting environmental records for volcanic activity and things like that. Also could provide things like drilling hazards. There's also things like melting. So if melting has occurred, this is a plus for habitability. We probably want to follow the water. However, if you melt a glacier, you melt the climate record within it. So that's a negative for climate record preservation. So there's going to be some interesting trade-offs that are going to have to occur, or even thinking about multiple different approaches and potentially different sampling sites for these mission aims. So it's quite a fun thing to think about, and hopefully these sorts of things will start to happen in the coming decades. And so I hope that what this has shown you is that the future of glaciology is probably interplanetary, and there's lots of fun to be had on multiple planets. And in this endeavour towards glaciology missions to Mars, glaciological expertise from Earth will be really vital for many reasons. And that's glaciological expertise deployed on Earth and on Mars. So on Earth, we still need to continue, obviously, understanding our own planet and how glaciers and glacial processes work here, because we really rely on analogous processes on Earth to understand how Mars functions. There's also many amazing things going on in terms of instrumentation and analytical techniques on Earth that are likely going to be required to be adapted for Mars. So glaciological expertise will be really useful for informing how we might adapt approaches from Earth and maybe design new ones for these kinds of missions. There's also a real need to start training planetary scientists and astronauts in glaciological field techniques as well as geological ones, and also trialing missions on Earth, like have a go at doing these sorts of things on Earth under kind of Mars-like conditions. And then there's also things that glaciologists can be doing on Mars, not least using the abundance of existing data to understand ice and climate processes, but also things like landing site selection. There's a wealth of expertise in the terrestrial community about what makes a good field site, how to use remote sensing, modeling, and analytical techniques to identify where might be best to land and sample on Mars, and then what techniques we might need when we're there. And then also before things like human missions, there's a raft of potential missions before this. And we really need to identify what those missions need to prioritize in order to maximize the chances of doing successful human fieldwork on Mars in the future. And there's lots of exciting science that can happen alongside that as well. So I hope that's whetted your appetite. There's lots to be done, and it's all very exciting stuff. And just before I end, I just wanted to plug that we've actually developed some tutorials for a free planetary GIS software called JMars, which you're welcome to use for research or teaching. This basically makes it simpler for students to stream planetary data sets all in one place without needing to download them or things like that. And just makes it a bit more accessible. So there's a QR code there, but you can also get it from YouTube afterwards if you want to have a go at playing with some planetary data. And with that, I'll conclude. So Mars is a glacial world. I hope I've convinced you of that. And there's a lot of international focus on ice for future missions in which glaciological expertise will be vital. And I hope that today I've shown you that structural glaciology is one such vital endeavour for ice access missions. Thank you.
Well, thank you very much indeed. Yeah, I think one of the reasons that Martian glaciology is so attractive is everything is so clean and tidy. There's none of the evidence appears to be destroyed by any of the things that mask our geomorphology on Earth. So thank you so much. Are there questions from the audience? We usually ask people to try and indicate on the chat, which I actually haven't got open just at the moment. There we go. If they have a question. So Felipe, do you want to unmute yourself and ask your question, or?
Sure, I can open my mic.
We can pretty much hear you, I think. It's not terribly clear, but go ahead and we'll see what we can do.
Thanks. Well, I'm Felipe Fuentes from Chile. I'm from the National Geological Service, and recently I'm studying about the rock glaciers here in the Chilean Andean, and the hydric contribution. So I wonder if there is more information about the Martian rock glaciers. I seem to see that more that they were focused on the white glaciers on Mars, but is there more studies about the rock glaciers over there?
Yeah, so there's actually, I've actually got it on the screen here. You might be able to see the little image in the middle of a valley, a small valley glacier.
Yeah, I saw that.
So this is something that I didn't actually show in my talk, and I probably should have done. There are thousands of these smaller glaciers on Mars as well. So the ones that I was showing are generally sort of tens of kilometers, even to hundreds of kilometers in size. But these are smaller kilometer scale features. They're below the resolution, the spatial resolution of the orbital radar. So it's a lot harder to constrain their contemporary ice content. So some of them look like debris-covered glaciers, but many of them may have lost more of their ice content than those larger glaciers as by percentage. So might be more like rock glaciers today. So there's probably a mixture of both is what I'm trying to say. But these smaller features currently are harder for the current instruments to study. But there's certainly, you'll know in Chile, there's an amazing range of rock glaciers that actually look a lot like some features that we see on Mars. So there are papers on these smaller features. If you search the term glacier-like form, you will find them. I hope that answers your question.
Thank you very much. Yes, that answers.
Thank you, Felipe. And David Mayer, would you like to unmute yourself and?
Sure. Dave Mayer, USGS Astrogeology. Dr. Butcher, fantastic talk. I was curious, what are the uncertainties on your ice layer orientation measurements, and would the range of things like possible dip angles have any implications for flow history or thermal history?
Yeah, so I obviously did as much as I could to constrain this because obviously orbital dip measurements seem a bit outrageous. But I did multiple repeat measurements of these, and I'm trying to remember the number off the top of my head, but it's on the order of a degree or two, the difference that I got. So obviously there's some unconstrainable uncertainty there, but they're certainly inclined at quite a significant angle. So yeah, I'm quite happy with that. I'm looking at your question in the chat. Uncertainties in the ice layer orientation. Are you talking about dip direction there, I assume?
Yeah, so for instance, like if there's like a whatever the 1 sigma is, let's say in your dip angles, is it possible that if in reality the angle is plus or minus is close to one of those extrema, would it have any implications for what was the flow history of this glacier, for instance?
I think I'm satisfied that they're quite secure. I don't think with the range of uncertainty that I got that it changes very much. The one thing I will say is that the one that's marked 11 degrees here is actually looking slightly into the side of kind of a spatulate structure. So I think the internal manifestation of these structures is actually more spoon-like. And we're not actually looking into the crest of that spatulate structure. We're looking slightly into the side of it. So 23 degrees is what I quoted for the divergence from the bed. But of course, when we're actually looking slightly into the side, so it might be a bit lower than that. So the dip of the structure is about 11 degrees, but the dip relative to the bed might be a little bit lower, just because we're not looking into the apex of that structure. But yeah, I'm not sure that it changed it with the uncertainties that I got, that it would change very much. Hope that answers your question.
Great, thank you.
Okay, we've got some questions on Facebook. So the only way I can do this is to read them, I'm afraid. So Celia is asking whether there is any evidence for iceberg scour in the northern primordial ocean.
Oh, interesting one. So unfortunately, fortunately or unfortunately, the northern plains are actually covered in very young deposits of ice, actually. So we actually see very little surface exposure in the northern hemisphere of ancient surfaces, just because these ice processes have really modified and deposited on top of all of that stuff. So unfortunately, I think the answer is probably no. But yeah, it remains to be seen, I guess.
Thank you. And then there are, I think, 2 or 3 questions from Gwyneth Rivers. I'm not sure where she's based. She might be able to.
Sheffield Hallam, I believe.
Okay, you know better than me. She said, "Thank you for such an interesting talk, Francis, and some beautiful imagery. I think I may have missed this, but what timescales were the obliquity cycles? And do we have an idea of the ice mass fluctuations in relation to this?"
Yeah, let me just go back. Ooh, quite a long way. So the timescales for an individual obliquity cycle are thought to be, sorry, I'm getting there, are thought to be around 120,000 years off the top of my head. So quite similar to the timescales we look at on Earth, but obviously with much larger magnitude fluctuations. So individual cycles around that, but also we've got these interesting timescales of this strange shift at about 5 million years ago. So the polar caps are thought to be less than 5 million years old or so. And then the mid-latitude deposits, you can form some mid-latitude deposits during that 5 million years, because you can see the obliquity does get up to 35 degrees at times. But most of them are probably formed earlier in Mars's history, and actually probably a bit earlier than 20 million years, actually probably tens to hundreds of millions of years ago. But in Mars timescales, that's actually quite recent, because it's effectively thought to have gone into its quaternary period. You might want to think of it as about 3 billion years ago. So this is one of the more recent processes on Mars.
Hopefully that answers her first 2 questions, but there's a third question there. She says, "I noted the glaciated impact craters and the upwarped thrust features. Are there any more glacial features unique to Mars?"
Ooh.
Sorry, I probably didn't intonate that quite correctly.
No, unique glacial features on Mars. Oh, that's a fun one. So the high latitudes of Mars have something that we call the latitude-dependent mantle, which is a very oblique term for blankets of icy dust material. So that's probably what that blue map that I showed of the neutron spectrometer shows, is extensive layers of icy dust that are thought to have formed in actually the slide we're looking at, in that blue period. That's those excursions to about 35 degrees probably didn't last long enough for thick glaciers to accumulate, but there are tens to hundreds of meters of this icy, dusty mantle that might record the mobilization of polar ice down to the mid-latitudes, which isn't something we really have on Earth, but it can get in the way sometimes, but it's also interesting in its own right.
Thank you very much. Are there any more questions from either the Zoom audience or the Facebook audience? I haven't seen any new questions appear on Facebook, so.
I have another. I can do another, David.
Go for it, Felipe. Go for it.
Thanks. I don't know if you show some data about the chemistry of this glacier. Have you pinched or have a sample of it? About
I missed that. Could you repeat that?
If you have a sample of the glacier, in one of the missions have measured or sampled the ice for chemistry or isotopes?
So the only mission that's actually hasn't touched but has exposed this perennial ice is this mission, the Phoenix mission, as far as I think I'm correct there. And this didn't sample the ice, but it had lots of instruments in its camera that were able to scrutinize its composition. But the mission concept that I mentioned, called Mars Life Explorer, would aim to go and actually drill into ice, so actually start to analyze the ice deposits and sample them. So that would be a really exciting first step towards sampling ice on Mars.
Thank you very much.
So there's a question from Roland that's just arrived on the chat.
Yeah.
Roland, do you want to unmute yourself, or?
Hi, Tavi. Yes, I'll try that. Got no idea what you're seeing anything from me. I'm doing this on my phone because the power got turned off here just as the seminar got underway. Fantastic talk, Francis. I'm very interested in what this glacier might have looked like before that gully cut through it, which in some sense is, given the slow timescale, it's probably what the layering that you're seeing is. And so my question was whether you had contemplated a somewhat more speculative model of what the glacier would have looked like before it got sliced through by the gully.
Yeah, so the gully is actually right on the edge of this glacier, to be honest. And I'm not sure it's really modified the glacier very much beyond punching through it where it has. So the gullies are actually on Mars. There's a lot of debate about whether they form by liquid water or actually carbon dioxide processes. And it actually is beginning to look like carbon dioxide processes can actually form gullies on Mars, which is rather alien. So this may well be a dry process, so not really modifying the ice beyond the gully itself. So I'm not sure that those structures are very much, I think, part of the original glacier flow. And effectively, you can sort of fill in the gully if you want to think about what the ice might have looked like before.
That's really rather what I meant.
Yeah.
That the face of the gully is not like the graceful Piedmont front of the rest of that face. I would have thought that there would have been, from your original image, that perhaps it's a matter of terminology, that there would have been another glacier coming in on that gully from the other side.
I see what you mean.
It's just that
no, I think it's
in terms of modelling, the stress conditions on that gully face have only, I would thought, relatively recently started to influence the flow dynamics.
Yeah, and they dissipate very quickly. So the effect of, we did look at the effect of the slope of the gully itself, and basically it's not really affecting it very much beyond the incision itself. So where we see that, like the apex of that arcuate structure, we're pretty sure that the horizontal, a long flow direction component is what's driving or driven that structure.
Okay, thanks very much. Just one other comment, that there's been at least one quite considerable horizontal ice coring project in Antarctica. I don't have the reference at my fingertips.
Yeah, thank you.
Cheers, thank you.
I think this might have to be the final question. Roger, do you want to unmute yourself?
Yeah, thanks very much for the talk. I just wondered whether any of the very little Martian seismic data we have so far had anything to say about ice thicknesses. I'm not sure where the landings were that had the seismometers. I know most of their endeavours have been going for very deep structure, obviously, but I think they tried some sort of local sources and that would look at very shallow structure.
Yeah, so you're thinking of the InSight lander, which is the only seismometer that's been to Mars, and that InSight lander mission ended last year, I think. So that actually landed nearer to the equator than the contemporary ice deposits. So it's done amazing things showing Mars quakes and things like that. The closest ice-related thing I can think of that I've currently seen in the literature is that it actually detected one of those ice-exposing impacts. So they've actually been able to connect seismic signals to an impact crater, fresh impact that was seen to have exposed ice. I don't think, or I haven't currently seen anything about ice thickness as far as I can remember. But watch this space, I guess.
Yeah, it just is. It's likely to have a very different size. If it's anything like on Earth, it'll have a very different seismic velocity to near surface, lithic debris and weathered sediments and so on and so forth. But yeah, smashing. Thanks very much.
Thank you.
Well, that's time to wrap up, I think. Yes, Happy New Year to everyone, as Roger said. Thank you very much for another really fascinating and very clear seminar, Francis, and some really good discussions. So thank you to everyone who participating online in various ways. And just to say that next week's seminar is one of our sea ice themed seminars. And we have Dr. Damien Ringison, who's a postdoc at NASA GSFC, who's talking about LKF's intersection angles in sea ice, a topic of which I know very little. So look forward to that. So thank you very much to our speaker, and thank you very much to everyone in the audience, and see you again soon.
Thanks very much.
The recording will be up on YouTube in a couple of days, I guess. So thanks very much to everyone.